Now we should be looking at what is in the RT box. On the left hand side of this picture you will see the inertial measurement unit. As you'll see, the Pentium processor is at the bottom of the right hand corner. The top board contains the connections to the IMU, the front panel power supply, and the Pentium processor and the two cables to the GPS cards. The RT has been constructed to operate in high vibration and high shock environments. The connectors are suitable for high vibration, and also the glue is used to ensure connections do not fall apart. What does the RT measure? The RT measures position, velocity, acceleration, orientation, for example heading, pitch and roll, the angular rates, angular accelerations and the slip angle. The core measurements are made by the RT. Other values can be computed from the fundamental measurements. Now we shall look at position measurements. The position measurements include latitude, longitude, altitude, the X position and the Y position, and also the distance. The position measured by the RT is in the WGS 84 coordinate system. The outputs are latitude, longitude and altitude in this coordinate system. Conversions to the other coordinate systems may be required, for example OSGB 36 in the UK. The RT can also output positions in meters on a local grid, but only if the local coordinates are defined before use. Because the Earth is curved, it's not possible to have a measurement in meters that covers the whole Earth's surface, so the RT must take a small section of the Earth and assume it is a flat section. To use the local grid, geoidal constant gravity surface, the latitude and longitude of the origin, or X equals 0 or Y equals 0, needs to be entered into the RT configuration software. Then the X and Y position measurements are output on the canvas. The RT also integrates the horizontal velocity to give a distance measurement. This measurement always increases. We shall now look at the velocity measurements. The RT measures the velocity measurements in, for example, the north, east, down, forward, lateral velocity. Also the horizontal speed and the 3D speed. Velocity can be measured in two ways, such as north-east, like GPS, or forward or lateral, like optical speed sensors. The RT measures true heading, so it is possible to separate forward velocity from the lateral velocity to give horizontal velocity. In the example here, the aircraft is flying straight into crosswind. The track or course over ground the aircraft takes is not the same as heading because of the crosswind. This is the same effect as slip angle in cars. The heading of the car is not the same as the angle of the velocity vector. To measure the track angle, you will need to measure the heading minus the tracking angle, which will equal the slip angle. The underlying calculation in the RT integrate the accelerations to give north, east and down velocities. Now we shall look at the acceleration measurements. The RT measures the X, Y and Z acceleration, also the forward, lateral, down and lateral slip rate. The RT accelerometers measure in the X, Y, Z directions of the vehicle. When the vehicle has some roll angle, then the Y acceleration has some component of gravity in them. The RT knows the roll and pitch angles very accurately. so it can rotate the XYZ accelerations to give forward, lateral and down accelerations. The forward and lateral accelerations do not have any component of gravity in them. The lateral acceleration is the roll-corrected acceleration. The lateral slip rate is an acceleration that measures how you are deviating from the perfect circle. Now we should look at the orientation measurements of the RT. The RT measures the heading, the pitch, and the roll angle of the car. Now we should look at the angular rate and angular acceleration measurements of the RT. The angular rates and angular acceleration of the vehicle can be measured about the body axis or the level axis. Note that the directions of the drawing are not necessarily correct. The Euler rates are as following: roll rate equals X rate, pitch rate equals lateral rate, the Euler rate equals the down rate. The angular acceleration are in the same directions as the angular rates. Now we shall look at the RT coordinate system. The conventions used by the RT are those adapted by most navigation systems. Engineers who work with vehicles tend to have the Z-axis pointing up rather than down, and therefore the Y-axis pointing left rather than right. Using the RT strut, it is common to mount the RT with the Z-axis pointing forward in the vehicle and the Y-axis pointing left in relation to the car's forward motion. It is important to note the orientation these axes are pointing within the car for use later during the software configuration. Ensure that the correct orientations are applied to the RT outputs in your coordinate systems is different. Now let's look at the RT outputs. The RT has several output formats. The RS-232, this normally transmits a binary protocol that we call NCOM. This is specific to RTs. We provide a C code drivers to help you if you want to decode this yourself. If your system is designed to go to a steering robot, then the RS-232 may be configured for a different output format. The Ethernet. The NCOM data is also transmitted using the NDB broadcast over Ethernet. The CAN. The CAN output is suitable for connecting to many data acquisition systems. Several CAN DBC files are provided to make it easier to connect the RT. Analog. The RT ANA module can convert CAN messages to an analog voltages. The RT outputs 4 special CAN messages for the RT ANA. The RT ANA just converts the data in these messages to an analog voltages. The RT is responsible for configuring the channels on the RT ANA.